Today, I want to welcome to the stage Nico from Geometry Research. Nico, you may know him as my sometimes co-host of the Zero Knowledge podcast, and he is one of the members of the newly formed Geometry Research. Hi, Nico.
Hello. How are you?
I'm good. We're behind schedule, but I hope we can still jam in as much ZK jargon as possible into this session. It's Geometry Research. I mean, folks have heard geometry before, but maybe you should tell them a little bit about what Geometry Research is.
Yeah. So it's a new organization. It's a new company. It's the same old research team you might have known from geometry, but we are now collaborating sort of independently. So we'll still be working on open source cryptography, protocol design, implementation, and security analysis. And I invite you to go check out our website, geometry.dev, or we have Kobe wrote this very nice thread sort of explaining the stuff we do on Twitter, X, and the handle is __geometrydev __.
Cool. Today we're going to be talking about the ZK Jargon Decoder.
Oh.
And this is a website that you built some time ago. I remember when I discovered it and I was like, this is so useful. Can you share a little bit about what inspired that? And actually, I think we just shared the link if people want to see what we're talking about here with the ZK Jargon Decoder.
Yeah, this was something I started writing out kind of for myself as I was learning ZK jargon and as I was finding all these like words that were very specific to ZK, but somehow weren't used in the same way many times. And the goal was just to have kind of like a little reference for myself. And eventually I thought, you know what, let's just put it online, see if it's useful to anyone.
Nice. I thought of it sort of like a glossary of terms. Is that correct? Yeah. Is that a good way to think about it? Or?
Yeah, I'm worried about saying that it's too much of a dictionary because it's not. Like the definitions aren't perfect. The point is like to be a bit more informal, a bit more practical, like to make sure you can read and quickly grasp the concept that is behind the word. And then, yeah, you might need like the specific mathematical definition. It won't be there.
Okay, got it. So we, in prep for this, maybe just to describe what we're going to be doing, we're kind of doing a live version of the ZK Jargon Decoder. So our goal here is to talk about terms in ZK that you may have heard but aren't completely familiar with, maybe comparisons, conflicts of naming where like two things sound similar but might not be. We have quite a few questions ready to go, but we are relying on you as an audience to also give us questions that we can talk about on the air on here. We tried on Twitter to get some questions and there were a few, but it was a bit of a fail. So please share some questions here. And just so you know what will happen when you do, we are able to bring up your comments onto the screen itself. So for an example, someone really liked your paper. Taras, thank you for mentioning that. And so this is kind of how we're going to be interacting with you folks. So please do think of great questions, put them in the chat. We're going to be, trying to keep our eyes on it. If there's too many questions and you feel like yours is maybe lost, feel free to post it again as well. All right. To start off, I know we had some questions that we wanted. So we wanted to sort of take the ZK Jargon Decoder site and at least start from there, and then we can kind of expand. So the first question was actually a question you thought, you felt you wanted to start with, which was, what does it mean to prove? We talk about proving a lot, but what does it actually mean?
It was also like the reason I wrote that one was because I found there was a lot of vocabulary and there was a lot of like context that I needed for some of the other definitions, and so I've had to put that on. I do have some slides if you can bring those up.
Let's do it.
Amazing. Cool. 1 second, sorry. Does this show up? To prove. Okay, awesome. So what we have is like in mathematics, we have statements that are either true or false. And the problems we're confronted with is like decisions. Like, can I decide whether the statement is true? So sometimes that's easy. Like you'll have a statement like the number 54 is even. Sure, I can look at it and figure that out. And sometimes it's hard. The number, this big old thing can be factored. And by just staring at it, I can't really find the answer. But if someone knows it, they can prove it to me. So in this case, yes, the statement is true, and here is my proof. And I'll give you the actual factorization of the number. And you can go and type that into a calculator and see that works. And that's a proof. That is it. I am giving this extra information that allows you to decide your statement.
Nice. All right, next up we have another question that you also mentioned in your website, which is probabilistic and interactive proofs. What are these?
Yeah. So this is kind of like the next logical step is like, okay, a proof is I give you this information, you check if your statement was true. The problem is sometimes proofs are going to be long. And I took like this Wikipedia screenshot, like a list of long mathematical proofs. And some of them are like 500 pages, 200 pages. God. And this is actually one of the motivations for like zero knowledge proofs at one point in academia. It's like, how can we make proofs that are shorter or easier to verify? And one way of doing this is by having interactive proofs. So rather than just like, oh, I give you all the information you need to verify the statement, we'll have sort of a conversation. And the verifier is going to ask questions, and I put those into quotation marks, to check that the prover keeps her story straight, right? So you can think of it like as an interrogation. And you ask a question, the prover gives an answer, you ask another question, and we keep going. And at the end, you check, all right, are these answers consistent with each other? So that's one way of doing it. Essentially, rather than you giving me a proof, we're going to have a conversation and you explain to me why something is correct. The other way of doing it is a probabilistic proof. So in this case, we're sort of relaxing our requirements. I'm like, all right, I don't care if once in a while I'll accept a wrong proof, but as long as that's, just once in a while. And in that paradigm, I can get away with not reading the whole proof. Like sort of how we as high schoolers, that's how we think of our teachers, like reading through our exams and like not reading the whole thing and be like, oh, sure, fine.
Close enough.
Yeah. So that's probabilistic proofs. And then we can also combine both. And that's what we call IOPs, interactive oracle proofs. And that's what we mostly use in ZK today.
I remember, just as an aside, I remember when I first, the the billiard ball example where you're like putting things. So that's like an interactive proof, but it's also probabilistic. Like I'm wondering, is it like you're interacting with someone, but you're also kind of like showing that like it would be very unlikely that they were able to lie that much?
Yeah, so I'm not sure what analogy you're referring to. The one I knew of billiard balls was for elliptic curves and the discrete logarithm problem, in which case it's more about like, why is a problem hard rather than what is proving.
Okay, maybe I'm
it's
thinking of something else, but okay. All right.
If someone knows
up,
the
if someone should say in the comments if that is an interactive probabilistic proof or not. Maybe it's not. One of the questions that we have is, what is a zero knowledge proof? And on the ZK Jargon decoder, it is not defined. Gaylord noticed this one. Why is that?
So you'll see also what I just said now about like probabilistic proofs and interactive proofs is not there yet either. And so essentially I sat down to write the zero knowledge proof and I was like, sure, that's going to be easy, zero knowledge, right? And I realized I needed all this context. And so I started writing the, what does it mean to prove? And I'm now doing the interactive and probabilistic proofs. And once we have all that baggage, we can go to zero knowledge.
There we go.
What is a zero knowledge proof? It's a proof where the prover's messages don't leak information about the stuff the prover knows. Very vague, but yeah.
All right, what is the difference between a proof and an argument?
That's a good one and a confusing one. It's basically a question of, we have these protocols, someone is producing a proof, and maybe they have incentive in tricking the verifier, right? Like if you produce a proof and get some money based off of that, you might want to trick the verifier. And so the question is, who are we protected against? Like what security guarantee do we get? Is the attacker anyone in the world? Is the attacker like something specific? And so in the case of a proof, the adversary is anyone, has unlimited computational power. Like, I don't care how many computers you have. I don't care if you have a quantum computer. You will not be able to break this. And again, let's be careful about what assumptions we make. You know, you can have proofs assuming that hash functions cannot be reversed. I don't know. So that's a proof. An argument is a bit weaker. We're only protected against someone who has a bounded computational power. So this is someone who uses regular hardware. And so for most things, arguments are fine because we have this sort of assumption that no one will ever get to like huge hardware, essentially. And in that sense, a proof is an argument because a proof protects you against these weaker adversaries and these stronger ones, but the argument is not a proof. Does that make sense?
Sure.
Cool.
Maybe for the audience, I actually want to ask, I want to bring up one of the questions that folks have asked in the chats, because I feel like we have some interesting ones. And I don't know if you're ready to do it, because this is a little bit, spontaneous. But okay, one is about, I wonder if you could do this. So this is from Nicholas. Hi, Nico. Could you please explain in a non-technical way why we need elliptic curve pairings and how they work?
Yeah. So I'll give you the why we need them. The how they work is going to be a bit harder. Why we need them. So in the first place, we use elliptic curves because we have this thing called the discrete logarithm problem. So I take a point on a curve. It's like you draw a circle and you take a point on the circle. So here it's not a circle, it's just this big elliptic curve. And we've designed a rule about like if I have 2 points, I can add them together and get to a third point. Great. I can add as many times as I want, and I'll just cycle around the curve. We can't multiply though. And so in our protocols, when we commit to things and want to add them together, we can do that. But if we want to multiply commitments, we cannot. With an exception, if you have pairings, you're allowed one multiplication, just one. So that's the why we need pairings. They give us this magical, like in a land of additions, we get one multiplication.
Interesting.
How they work is a lot harder.
All right. Here's one. What is a polynomial IOP?
Yeah.
There's further questions to that, but maybe we just start with what is a polynomial IOP?
So we saw earlier what is an IOP, interactive oracle proof. It's this combination of interactive proofs and probabilistic proofs. So it's multiple rounds, and with every round the prover says something, but the verifier only checks a small part of what the prover said. In a polynomial IOP, the prover can only say polynomials. So the prover sends polynomials, and the verifier doesn't need to read the whole polynomial and can just evaluate the polynomial at a specific point. Can you explain NTTs and FFTs and the usage? Yes. They are, so FFT is many things, but it is amongst all its uses an algorithm that takes a polynomial in its coefficient form and evaluates it over a bunch of different points. Or we could go the other way around. We take the evaluations of a polynomial and go back to its coefficients. If we work in finite fields, etc., we no longer call it an FFT, we call it an NTT. But it's kind of conceptually the same thing. It's just two different names. And NTT is the more precise way of saying it, but no one is going to be mad at you if you say FFT.
Are they both the same direction?
I always get it wrong. But yes, NTT is the same direction as FFT, and inverse FFT is the same direction as inverse NTT.
Okay.
But I always forget who's who. I think FFT is from coefficients of evaluation, and inverse FFT is the other way around. But yeah, correct me if that was wrong.
Yeah, someone in the chat might know this. Cool. I have a question that sort of follows on this one, which is polynomial IOP and polynomial commitment. So we've heard those terms. Is there anything that is non-polynomial that could be used instead?
Yeah.
Like, why are we saying
so
polynomial in both these
yeah,
cases? It
yeah.
seems like there might be non-polynomial IOP or non-polynomial commitment.
And yeah, you're absolutely right. The reason we like polynomials so much, it's because they have this sort of error amplification property or distance amplification. That's what people like to say. So say I take two polynomials that are the same except for like one of the coefficients. And I evaluate those two polynomials at some random point. What happens is I'm going to end up with wildly different evaluations, even though the polynomials were super close except for like one difference. So that's why we like polynomials. But there are other objects that have this sort of amplification property. One of them are like more generic error correcting codes. And that's sort of, if we go back to the earlier, like I think Lehero or like the original Stark paper, that's sort of what it was based on, even though the codes they use are like polynomial based. But you wouldn't say it uses a polynomial commitment scheme, for example.
Okay. And Fry generally is always lumped in this polynomial commitment category, but I always hear it's like not exactly a polynomial commitment. So what, like, would that be an example of a non-polynomial?
Yeah. So Fry tells you whether or not a commitment is indeed a commitment to the evaluations of a polynomial. But it's not exactly a polynomial commitment scheme, right? Because in a commitment scheme, I want to be able to evaluate the polynomial anywhere else. So to build a commitment scheme from Fry, you need to do a bit of extra work. So Fry is lumped in as long as you do that bit of extra work and that you do things correctly.
Is it mimicking a polynomial commitment? Or is it like you're adding a polynomial part on top of it or something?
You are... I'm not sure how I would like give you the image. It's more...
Okay.
It's I run Fry on something that was not the polynomial I intended, but something that tells me something about the polynomial I intended.
Okay.
So for those who are familiar with KZG proofs, KZG has like this opening quotient. And when we want to do polynomial commitment schemes from Fry, we do Fry on this quotient. But that is, I guess, an answer for people who know KZG. Other jargon term that people might want to ask about.
There was a question that we had actually, someone just asked a question and we had kind of prepared a very similar question. So I'm gonna do our part and then add theirs. So we often hear of a ZKP as being consisting of three parts: completeness, soundness, and zero knowledge. There's sometimes a criticism of people calling ZK snarks ZK snarks when they're actually not using that zero knowledge part of the ZKP. But yeah, someone asked, let me just find this. Can you please explain the difference between general soundness and knowledge soundness? So in the kind of list I shared, that's general soundness, completeness, and zero knowledge. So maybe we should start with like a definition of what knowledge soundness is, and then why are there these two kinds of soundness?
Yep. Glad you asked. The slide is ready to go.
Yeah, we were ready for this one.
And so here, the difference between soundness and knowledge soundness is what does the system guarantee? So earlier we had who are we protected against, but what's the guarantee that we get? So in the case of soundness, we know that if an honest verifier accepts a proof, then there exists a witness that satisfies the instance. And I'm throwing in these words, witness, instance. This is sort of stuff I cover in the what does it mean to prove. But if we go back to our, sorry, I'm jumping around a bit, but hopefully this will have a nice payoff. Our statement 2 earlier that we wanted to prove, we say the number something can be factored. This something, we could actually plug it in out and put something in, right? I could say the number 5 can be factored, or the number 9 can be factored. Some of these will be false, some of these will be true. So this thing that I plug in is what we call the instance. The witness is what we would call the proof. In the sort of non-interactive, non-probabilistic setting, the witness is this proof, is this information that tells me that my instance could be in a true statement or is in a true statement. All right, so I guess we can stay here for the example. Soundness says, if I've accepted a proof that the number thingy can be factored, then this thing must exist. This witness must exist. Great. Whoops. Knowledge soundness is a stronger requirement. Now I'm saying if the verifier accepts the proof, then the prover knows the witness. So back to earlier, yeah, it's not good enough that the factorization exists. I need the prover to know it.
To know the like answer to it, the actual numbers.
To know the actual answer.
So you can't use like a heuristic, like, oh, it will likely be
exactly
factorable,
no, we can't do that.
but I don't know I don't know what it exactly is. In this case, you need to actually know the values.
Exactly. Yeah, say our instance was a super large number that ends in a 2, and I ask you, can this be factored? You can very quickly say yes and prove it to me, but you don't need to know the factorization, right? So that's a difference. And again, knowledge soundness means you also have soundness, because if someone knows the witness, then the witness must also exist. But the other way around is not true. The witness exists, but maybe you don't know it.
In which cases do you need knowledge soundness?
Yeah, I actually have a little example case. And this is something that came from the ZK whiteboard sessions. Like there's a study club that you run in like the ZK Hack Discord. And this question I came across a lot. And so we sort of came up with this example. So let's say I want to prove that I know the private key X for some public key capital Y. So this is like a very concrete like blockchain example. So the valid key pair should have Y equals G to the X. And discrete log, it's hard. If I give you Y, it's hard to find X. Great. So we have this instance, which is Y and G, and we have a witness, which is X. And the question is, do I need a protocol with soundness or knowledge soundness?
Are you asking me? No.
I'm asking either you or the chat, I guess.
Okay. I don't think I can answer it, but let's see. We can leave it in the chat. Yeah. In this case, do you need a protocol with soundness or knowledge soundness? I'm curious if the crowd can answer this. That'll be interesting.
There are some other good examples I see in the chat, actually.
Really?
Yeah.
Knowledge soundness, first answer.
Yeah.
Why?
All right. That is correct. Why? So the witness, the private key, always exists. Like if someone gives you some public key Y, there is always a private key that corresponds to it. And it doesn't matter whether the prover knows that private key or not, like it always exists. So if we had only soundness, then anyone could make a proof that the private key exists, because that's true. If we have knowledge soundness, on the other hand, only someone who knows the private key can make the valid proof.
It's funny, in the group, there's definitely been some people who understood it differently, but thanks for defining that, Nico. I feel like we've gotten a whole conversation going. It's really fun to see everyone debating this. It's awesome. Shall we move on?
Yeah.
Something I just realized we forgot to do at the beginning of this was give a little bit of a framing for the kinds of questions we're choosing. So you may have noticed I've been picking some and maybe not picking others. Generally, we're looking for a little bit more general questions, something, definitions, jargon, decoder kind of stuff. Nico, maybe you can also share what we're not going to be looking for, what's maybe not really suitable for the jargon decoder.
I mean, right now, like the decoder itself, we won't explain like in detail how Plonk works, right? We might say what Plonk is, but I won't give the inner workings of it. Similarly, I'm not going to look at, like it's very ZK and cryptography specific. I'm not going to look at like system stuff or consensus stuff. So questions like rollups or validiums, like completely, for me, like out of my knowledge, essentially.
Cool. So I have another one I want to kind of continue with that we had pre-prepared, which is about
Oh, actually, wait. Sorry.
Oh.
Before we move on, there was this one thing I really wanted to show.
Okay. Oh, yes.
Sort of summarizing this conversation of proof versus argument and soundness versus knowledge soundness. So on one axis, I have who are we defending against? Who's our adversary? And people like to use these terms computational or statistical. So when the prover has unlimited computation, we have statistical guarantees. Like essentially, if the verifier goes wrong, it means that the prover got very lucky. And in the argument model, we talk about computational guarantees because we only have guarantees if the prover is computationally bounded. And then on the other side, we have soundness, the witness exists, or knowledge soundness, the prover knows the witness. And so now you can start coming up with all these different words, right? Like if your adversary is unlimited and you just need soundness, that's a proof. If your adversary is limited and you just need soundness, you have an argument. If your adversary is unlimited and you need to prove knowledge, that's a proof of knowledge. And people like to use POK. And if your adversary has limited power, but you still need to prove knowledge soundness, you have, knowledge soundness, you have an argument of knowledge. But the reason I drew this is because there's a bunch of other acronyms that we usually find, and I wanted to sort of place them on this map.
So cool.
So hopefully people will recognize some of these, like ZKP. Well, all right, it's a zero knowledge proof, so I have that in the proof box, but it's not a proof of knowledge.
Yeah.
And for that we have a ZKPOK.
And the snarg, like I remember that definition from actually, I think it was the first ZK hack. We had Alessandro who was using that term. And I remember being like, why don't you just say snark? It's because it's a different concept, slightly.
They prove different things.
Yeah.
NISC is one that people often see, non-interactive zero knowledge. And this one I have it on the border because the acronym itself doesn't specify if it's a proof or an argument. Usually when people say NISC, they mean a non-interactive zero knowledge proof. So it's usually more on the proof side. But yeah, it's sort of ambivalent.
Very cool. This is such a great graph. I know a lot of folks are asking for, like, there will be a video of this. I feel we could probably share these slides after, right, Nico?
Yeah, absolutely.
We will be sharing the Jargon decoder. We did share that link earlier in the chat. Maybe we can share it again here so people can keep their eyes on it. We're going to keep going, and we're seeing some really good questions come through. One person asked, I think this we could talk about here, which is finite fields. What is, let me pull it up. So what is a finite field? Because we hear that finite field a lot in this world. And why is it important in proof generation or verification?
Yeah. So a finite field, you might have worked with them. So you've worked with fields for sure, because the real numbers, like the numbers that we use all the time, the numbers used in high school math, form a field. So that means you're allowed to add them together, multiply them together. You can divide everything except you can't divide by zero. Big no-no. There are a few more rules of what forms a field. But yeah, this is not a math class, right? Like that was the point of the Jargon decoder. Finite means that there is a fixed number. So again, the real numbers, the ones we used in high school, they go up to infinity. They're not finite, they're infinite. Finite fields, we have a cap. And what happens is when we reach the cap, we loop back to the beginning. And that's a very important property for us. This looping back means that if I ask you to take a number at random within that finite field, there are no numbers that are more likely to be picked than others because we have that loop back. And if I ask you to pick a number, pick another number, add them together, it still looks completely random, which you wouldn't have in something that's not finite. So that's why they're important. They give us this property that we can sample things at random, process them, and the output will still be sort of random looking. The other property that they have is that the discrete logarithm problem is hard. So we have these hard problems that come from finite fields, and we can also build curves, elliptic curves over finite fields and get even harder problems. And cryptography relies on hard problems to work.
What is an alternative to a finite field? Like, are there other systems built on other things?
This is where I'm exposed for having no cryptography culture. Let me see. No, I think most of cryptography is based on finite fields.
And when we talk about things like small fields, are they all, actually have a question for this one. Are these always small finite fields still?
Yeah, they're still finite.
Okay.
And well, that's why they're small, right?
But like,
Because
not all finite
they are
fields
finite,
are small
but they're
fields.
even more, sorry?
Right? Not all finite fields are small fields.
No, exactly.
Okay.
But the small ones have to be finite.
Okay.
Otherwise, if it's infinite, then it's big, right?
All right.
So it's just a matter of, how I said, when we pick a finite field, we choose like a maximum and then we wrap around. Small fields are ones where the maximum is small.
Okay.
Yeah.
So I guess that sort of defines here what is, when we talk about
what is a small
are they?
field is like we choose our maximum value to be something small enough. Usually we like to keep it small. We usually mean under 64 bits or under 32 bits. So it's stuff that we can store nicely on our hardware.
Maybe a follow-up there is why small fields?
Yeah, well, I guess I sort of alluded to it here, but we can store it nicely on our hardware. So why small fields? Yeah. Why did we not use small fields at first? Because we do like picking things at random. And then, what was the chance that you pick that thing is 1 over the total number of elements. So if your thing is too small, this chance becomes quite big, right? If our field has just 2 elements and I ask you, all right, pick a random number between 0 and 1, I have a 50-50 chance of guessing which one you picked. But now if I ask you, all right, pick a random number between 0 and 10,000.
Yeah.
This gets a lot harder for me to now guess. So that's why, for security reasons, we like big fields.
Okay, things get lost.
But for efficiency, we like small fields.
Interesting. Cool. That's a good trade-off.
Yeah.
Or good to know.
Well, and that's actually a super interesting part of the recent advancements in zero knowledge is how do we benefit from both? How can we still use small fields but not lose security?
That's cool. I have another question from the crowd. This is about blinded polynomials. Are you familiar with blinded polynomials, Nico?
Yeah.
So how does
if it is what I think they mean, then yes.
Okay. How do blinded polynomials work? Can you please explain how roots of unity help in a domain?
Yeah. So let's start with this idea of blinded polynomial. So let's say for some kind of proof, let me figure out how to phrase this. All right. Let's say for my proof system, I need, I have a bunch of values, like 10 values, a vector of 10 values. And I can take these values and get a polynomial from it. Great. Now that polynomial reveals information about my values. Can I somehow change the polynomial, but still make sure that it represents the right values? And that's what we do when we blind these polynomials. And this is something you'll see, for those who are familiar with Plonk, round 1 of Plonk, this is what happens. We blind our polynomials. And so how do we do this? We multiply our polynomial by something else that doesn't affect our polynomial on the values we care about, but affects it everywhere else. And that's how we sort of blind what it was, because we've now multiplied it by something. It's a bit hidden. It didn't change the important property that our evaluations are still the ones we wanted over that small vector. But we're not revealing our polynomial. Hopefully not too hand-wavy. Roots of unity, how do they help in a domain? Well, like we just said, like this finite field is this nice thing that loops around. Roots of unity in a finite field is just saying like, okay, I still want to loop, but I don't want to go through every step. So I'm going to take just 4 steps such that like going from one to the next, to the next, to the next, I've looped back to the beginning. That's our roots of unity. And you can draw that like on, the unit circle. I don't know if you are familiar with this from high school, or maybe a bit after, I don't know. So that's how they help. They allow us to work in smaller sets of our finite field, but still keep the nice loopiness.
All right. I want to ask another question on that we had prepared. One, this is about circuits. So a circuit is mentioned a lot. What is a circuit? And are all ZK systems built as a circuit?
Yeah, I guess the tab I have open next to the slides sort of gives it away.
Circuit. Jargon decoder.
Yeah. I thought I would use it, and I guess, shameless plug. I guess this whole thing is a shameless plug. So circuit, usually we mean arithmetic circuit. So it's like an ordered collection of additions and multiplications. So this little diagram shows you the circuit. Sorry. So we have at the bottom these inputs, x0 to x2. We have up here a single output to our circuit, y. And we see like there are some built-in gates, these multiplication and additions, and there are some, you can even have like hard-coded values inside it. And now each of these wires has a value on it, and we can work our way through it and evaluate things. So down here we have x1 plus x2, then it gets multiplied by 3. On the other side we have 5 plus x0 and times x0, and then we add it. And so we could also write it as an expression, right? So that's what a circuit is, essentially like a sequence of operations. Why do we care about them? Was that the rest of the question?
Are all systems built as a circuit?
Yeah. So I guess actually relating this back to what are we proving? We can prove many things with the circuit. We can say, is 10 a possible output for this circuit? And in that case, the prover would have to find these x values that make it go to 10. Or you could say, what is? Or you could be more strict with it. Like, is 10 the output when x is 5, x1, like you get to choose essentially all these values that stick out of the circuit. You get to ask questions about. Are all ZK proofs built on circuits? No.
Or built as circuits? Like, are they all, like, is that the underlying mechanism for all ZKPs?
No. So the reason we like circuits is because we have found that any provable statement can be expressed as a circuit. And then if you can make a proof of knowledge, or an argument of knowledge for a circuit, then you can do it for any provable question. So that's why we like circuits. But it's sort of inefficient, right? Because maybe my state, like if I have something I'm trying to prove to you, and it's something simple, I don't need to convert it to a circuit and then prove the circuit. Maybe I can just prove it without going through that extra circuit step. So are all ZK systems built a circuit? No. One example is if people have heard of Schnorr signatures, those are actually based from, like, they're the non-interactive version of a ZK protocol that we call the Schnorr identification protocol. And that thing doesn't use circuits, for example.
I had a follow-up to this is are error-based systems still considered circuits? Because what we learned from like the ZK whiteboard sessions was, they like what we have in front of us looks like a circuit, works like a circuit, but error has this very different looking thing. Like it
looks like a table, right?
Yeah. So is it still a circuit? Or is it still built on a circuit? I think I want to try to use the terminology right there.
So you know how I was saying circuits capture all provable statements? Error captures all circuits, therefore captures all provable statements. But similarly, R1CS captures all circuits and therefore all provable statements. Like you have this sort of these boxes. So in a way, they're not the same, but they're the same. Like that's the sort of unsatisfying answer. you can express any circuit as an air. You can express any air as a circuit. It's just a translation. So it's hard to answer, are they the same, right?
Okay.
There's a really good article, actually. So actually, no, first, let me backtrack a bit. They do express circuits. And yes, an air-based system does prove something about a circuit. But the circuit is not in this pretty diagram form, it's in this table format.
Got it. I'm going to close that one down. We have a lot of questions coming in the chat, so I feel like we should go through some of them.
Yeah.
So somebody asked about folding, which I don't think, have you defined folding in the jargon decoder?
I have not. There's a whole to-do list.
Okay, there's a whole to-do list. All right. I wonder, actually, Nico, do you need help with the jargon decoder? Would you be open to people
absolutely.
creating some
if people
of this?
want to like contribute, collaborate, happily, definitely.
Cool, because even in the chat here, I see some people answering other people's questions, and there's some interesting stuff there we might be able to dig up.
I mean, the rules are simple. As long as, basically, I always try to keep this one-liner or one sentence, let's say.
Yeah.
For quick reference, and then a bit more of an explanation, and then that's it.
Cool.
And yeah, from this page you can get to the repo, and there you can start like contributing. Cool. So folding. If we go back, let me go back to here, our approval statement, statement 2. So in this case, we had one instance, and the proof is like one witness. Great. But what if we had, I don't know, 20 of these, can this thing be factored? And the verifier doesn't want to, every time it's given a witness, check the multiplication and see if it works. So how do we sort of solve this, or how do we get more efficient? We fold. We take 2 instances, combine them into one new instance. So in circuit land, it would be, let's say, we assign specific values to x0, x1, x2, and y. And we assign, I don't know, 10 different sets of these values. We can fold them all into one single circuit and prove that circuit. Yeah, recent progress. We have a bunch of different variants of folding, I guess. And the progress is usually in how many things can I fold together, or how fast can I fold 2 things together, or what kind of things can I fold?
And folding somewhat, like, isn't folding limited to KZG based? I want to see if I'm correct here. Like, there's certain kinds of snarks that can use folding, but not all.
Yeah, folding is, so the way we sort of combine 2 instances into one requires to add commitments together. And not every commitment scheme allows that. So elliptic curve stuff, we can add them together. Any hash-based commitment, we can't add them together.
Is this where, like, it needs, I'm going to see if I can say this, additive homomorphism?
Yep. Yeah,
okay. That's cool. Someone asked this is when we have actually a bunch of questions around the polynomial stuff we were talking about. So can we say circuit plus knowledge equals polynomial?
Ooh, no, because you could have circuit polynomials, but no knowledge. You could have a polynomial IOP, for example. So we're back to polynomial land. But that just has soundness. That does not have knowledge soundness. So in that case, we wouldn't have knowledge in that little equality there.
And then what you need. Okay, here's another one. This is just more theoretical. Can you explain why any of these things are using polynomials at all?
Yeah. So we touched upon it a bit earlier, and it was this idea of distance amplification. If I have 2 polynomials that are the same except for one coefficient, and I take a random point and evaluate both of these polynomials at that random point, they probably won't have the same evaluation. And that's sort of the property that we like about them, is even if you change the tiniest thing about a polynomial, it's going to be very hard to match my expectations. As in to match the unchanged polynomial.
Huh.
So yeah, and I remember, I think someone asked,
uh-oh. Did he close the browser? We'll give him a second to come back. This is good because I'm actually trying to sort. Hey, Nico. Hi.
I was trying to go through the questions and
click,
press
clear,
back.
click.
Yeah.
You gotta load your slides again, by the way.
Yeah.
If
someone was talking about when we last spoke of polynomials and this sort of distance amplification property. Someone rightfully asked, but wouldn't error correcting codes correct the error rather than amplify it? That's true, but to correct the error, you first detect it, and to detect the error, you use this amplification property.
All right.
Yeah, and someone, I think a few minutes back, talked about the Schwarz-Zippel lemma, which is kind of what I'm alluding to with this thing of distance amplification. If I take two polynomials that are different, evaluate them at a random point, it's extremely unlikely that they will have the same evaluation.
Cool. Let's see. So now there's a few on gates, and I know that this is a question from a little bit earlier, but what is this? So, because we're kind of flipping around a little bit, I think the questions to the gate stuff came after the polynomial ones.
Context switching.
Yes. How can a custom gate be represented in a current circuit graph?
So I'll bring back the current circuit graph. Let's say let's say very often I'll take my inputs and apply, I don't know, a hash. Let's say I very often do some hashing. And if I were to write a hash with these plus and times, it would be, I don't know, thousands of them. So rather than having every time I need a hash, copy pasting thousands of gates, I can say, all right, I bundle them into one, and this is my custom gate. And the cost of doing this is now just like one application of my custom gate. It might be very slow gates, but it's just this one thing. So that's how you would represent it here. A box with a different symbol. It's no longer strictly an arithmetic circuit, because now we have custom gates, and that's sort of the flexibility we get from R or Plonkish.
And was it Plonk that pioneered this, actually?
I, at least in modern snarks, yes. I don't know if, in this history of computing, like I would be surprised.
Okay.
There is a very good article by Ariel, and I'll try to find the link and probably post it in the Discord for ZK Hack. This article that sort of explains how do you go from R to what Plonkish is, and it shows actually how they're related and how R is just a special case of Plonkish.
Okay, cool. This one's about circuits as well. Is there always two inputs and one output for circuits?
Yeah.
What is the difference between gates and gadgets?
So is there always two inputs and one output? No. You can have as many inputs as you want and as many outputs as you want. And here I've drawn, what we call these fan-in 2, fan-out 1 gates. So fan-in 2 means two inputs, fan-out 1, one output. But you can have whatever you like. And the nice thing is, actually, our proof system doesn't see a difference between inputs and outputs. It doesn't even know that there's a direction. It just cares, is the value y related to the value, to all these x values in the way we expected. I think that answers. What's the difference between gates and gadgets? This is kind of specific to libraries, and everyone likes to use gadgets in their own way. But usually a gadget will be a collection of gates that have a specific use, a specific functionality. Like, all right, I've used gates to create something that, checks that a number is less than 10. This is now my less than 10 gadget.
Cool. I don't know if this is something you can answer over here, but can you explain how Plonk replaces elliptic curve pairings in proof? Is this true?
No. Plonk uses pairings. Plonk
Okay.
needs that sort of one multiplication that we were talking about earlier.
So it's not replacing it.
No.
It's
And it's, yeah.
Okay.
Well, actually, Plonk that uses KZG needs pairing. Plonk with a different polynomial complement scheme might not need pairings. Okay, so actually, let's dig into it. Plonk, so the pairing doesn't come from Plonk, the proof system. It comes from the commitment scheme. You can commit in other ways, and you can plug that out and replace the pairing. The proof system itself doesn't need that one multiplication. But yeah, the how this now gets into like sort of how Plonk works.
Okay, which we don't have time to cover.
But whiteboard sessions, I think it's episodes 1 to 3 cover that very well.
I think 5 we actually do. I mean, there's like Plonk detail. Although actually, I don't know if he does elliptic. He definitely does custom gates and gadgets, but I don't know if he does elliptic curve stuff.
Okay.
Cool. Just so everyone knows, we have 5 minutes or so.
Yeah.
So we may have to, I have a lot of your questions selected, but I don't know if we actually get to all of them. By the way, just want to say thank you so much for going through this with us. This is the first time we do a live ZK Jargon decoder, and we'd love to hear at the end of this how you feel about it. But let's continue because we have a little bit of time.
We can also take some of the questions into the ZK Hack Discord. I know you have a channel for ZK Hack 4, and I think I'd happily stay there for a bit and chat.
Nice. Cool. Okay, this is one that kind of goes back to the circuit question and air.
Mm-hmm.
So what does the rank in R1CS denote?
Yeah.
So this is again so when I mention air, it's a different format. R1, I always think of R1CS air as these are two flavors of, well, they're different actually, right? They're you're going to choose one depiction or the other.
Yeah.
You can move between them though, right? Could you depict something? Okay, you can. But in this case, we're looking at R1CS. Rank 1 constraint system.
Yeah, can bring it up. R1CS. And again, in the whiteboard sessions, there's a good session unrelated to R1CS, but where Mary Maller goes over how to use R1CS or how to do it by hand. And I have a link there. Sadly, the rank is property of matrices. And I am not good with my linear algebra. So this is a question for Guillermo, if you ever find him. He was doing this linear algebra and succinct proofs class in the ZK Hack Discord. I think his handle is at Guille. Maybe you want to fire that question at him.
Cool. Should I keep going? Should I add some more? Or do you want to?
Yeah.
Okay.
I mean, it depends. We are getting dangerously close to the puzzle release time.
True, exactly. Yeah. So just to remind everyone, in 7 minutes, we release the puzzle, and there is a little announcement about the puzzle and sort of the description that we still have to get to. But I think this one is quite general. So from Lori, which are the unique properties of ZK technology? Which unique properties provided that can't be accomplished by other easier cryptography?
Yeah.
Kind of why ZK here?
Yeah. And I guess, are we using ZK in the strict ZK sense, or what Tarun likes to call the royal ZK?
Yeah.
So
let's say
I'll
ZK,
give you both.
ZK. Let's use the strict actually. Why use ZK?
This was, well, I guess it's in the name, right? Zero knowledge, and it's this privacy property that nothing leaks. And this you can't get elsewhere. Although even encryption.
The MPC folks argue that zero knowledge is not zero knowledge because someone knows the secret, whereas an MPC, no one knows the secret, apparently.
So in zero knowledge, yes, we're not saying no one ever knows the secret. We are saying my secrets remain mine. as long as I want it. The question of can we create values that no one knows is a completely different problem. But MPC will use zero knowledge often in these protocols, because if we're interacting together, you have part of a secret, I have part of a secret, but we don't want to reveal our parts to each other, but we can't trust each other. Guess what? Zero knowledge proofs.
Yeah.
Yeah.
It does seem though there's sometimes like use cases that are proposed for ZK, for example, like private compute, where certain systems, if they were more efficient, like FHE, would make, and this I'm super quoting FHE people here because that's what they argue, but like they would argue that actually for certain kinds of private computation, it is actually better to be in a completely sort of black box private area and not be just sort of shielding parts of it. Maybe for complexity or how
they do different things, right? FHE is about, all right, I have some encrypted data. Can you compute for me on that data? Whereas a zero knowledge proof is I have some hidden data and I can convince you about properties of that data. The other thing we have to be careful about is encryption is not perfect. They rely on hard problems. They even let's say encryption that is not susceptible to like a quantum computer will be weak over the years, right? If I hack at it for 50 years and send my computer for it for 50 years, I'm eventually going to decrypt your message. With zero knowledge, the zero knowledge property is perfect. There is no chance for you to learn something about what I hid in my proof. I think you were looking at the time there.
Yeah, I'm kind of looking at the time. Also, I'm trying to find out if there's one more question I could put. I might actually grab one of mine. Or maybe one of the ones, actually, so this was one that came in through the Discord, which I think would be cool to answer. But let me I have to hide the current and then I'll pull this one up. So this one came earlier today regarding the front end and the back end of a snark. So we didn't really talk about this, did we? Like it's not polynomial and polynomial. Those are both.
This is a different separation.
Okay, are those both back end, polynomial commitment and IOP? Or they're just totally different paradigm?
No, they are. Yeah, they're both in the backend.
Okay, they are the backend. Okay.
Yeah.
So in this case, regarding the front end and back end of a snark, is the front end basically just the arithmetic circuit and arithmetization, and everything else is the back end?
Yeah. So the front end you can think of interfacing with the world. So let's say, how do I convert? Like, all right, I have a statement. How do I make that statement snarkable? And that's the front end. And what is it to be snarkable? So each snark has a different format, let's say. So you can use R1CS as a format. You can use error as a format. You can use whatever. The backend is once the proof system is given this sort of filled up circuit or this filled up error or this filled up R1CS, prove it. So yeah, front end is sort of arithmetization. And let's say I write a circuit in Circom. I use the Circom compiler. That's the front end. The output of that compiler can now be sent to a backend, a proof.
Cool. All right, I'm hearing, I think we have to get moving because people want to do the puzzle from what I've heard. Yeah, I think the puzzle, so the repo is private, but the placeholder's up. I'm going to share something that, puzzle time, exactly. Nico, thank you so much for doing the ZK Jargon Decoder.
Thanks for having me on, Anna.
Yes.
And thanks everyone for participating. I think this was great.
Yeah, next time we do this, we use the whiteboard.
Yes.
We didn't touch it. Yeah. There was a whiteboard idea, but it didn't happen.
Thank you. Quick fire, right?
Thanks everyone for those amazing questions too. It was really fun to see you're kind of like jumping into these topics. Thanks, Nico.